Good afternoon and welcome. Welcome on behalf of the university to this is the 4th annual celebration of the Teaching and Learning Symposium. I want to thank you all for coming because it is a testament to your commitment to good teaching, to excellence in teaching that you are here. And this, as you know, is an essential part of the university's mission: teaching, education, and research, along with service to the community, are the touchstones of Columbia's mission. So thank you all for coming. I also want to thank Suleiman Kachani, who is the Vice Provost for Teaching and Learning, and also thank Catherine Ross, who is the Executive Director of Columbia's recently founded Center for Teaching and Learning, and who's done a great job since coming here. Thank you both. This annual celebration is just that, an opportunity for the Columbia community to celebrate and learn about the innovative efforts of faculty and graduate students who are transforming their courses to enrich the student learning experience. I also want to extend an especially warm welcome to Professor Carl Wieman, our keynote speaker. Professor Wieman, as you know, is a Nobel laureate and professor of physics and education at Stanford University. He has pioneered the use of experimental techniques to evaluate the effectiveness of various teaching strategies for physics and other sciences, and recently served as Associate Director for Science in the White House Office of Science and Technology Policy. He also served as Chair of the Board of Science Education of the National Academy of Sciences from 2005 to 2009. It's great to have you with us today, Professor Wieman. Following Professor Wieman's presentation, we hope you will take full advantage of the exhibition in the Rotunda building just across the hall, which showcases the great work of Columbia faculty and graduate students at the intersection of education and technology. I'm especially pleased that some of the best projects, more than a dozen, resulted from teaching and learning grants awarded by the Office of the Provost this past year. Indeed, since the fall of 2014, it's hard to break old habits. Since the fall of 2014, we have awarded a total of 108 teaching and learning grants, supporting not only individual instruction, but the work of entire departments and schools to innovate and recreate, in effect, their own curriculum and their own teaching techniques. Later on this afternoon, we will reassemble to announce the inaugural cohort of the Provost Senior Faculty Teaching Scholars. So enjoy the afternoon. The exhibition is just across the hall. Thank you all for coming, and it's a pleasure to have you here.
Thank you, Provost Coatsworth. And thank you all for coming today. I am, like the Provost, delighted to see you all here and to welcome you to our annual Teaching and Learning Symposium. Provost Coatsworth mentioned a few things about our keynote speaker today. Whoops, I forgot my prop. To all of the honors and awards and positions that Dr. Wieman has held, he has also recently published a book, Improving How Universities Teach Science, Lessons from the Science Education Initiative. It's a great read, as you can tell from my sticky notes. Lots of great advice for faculty teaching in the sciences, but also across other disciplines as well, widely applicable teaching research. His current research is centered around expertise and problem solving in science and engineering, trying to better understand how we can measure and teach these deeply foundational and important skills. He's also studying introductory physics labs and looking at the ways in which traditional labs are ineffective for learning and showing how they can be improved. Without further ado, I would like to present to you Dr. Carl Wieman. Dr. Wieman will speak for approximately 50 minutes, and then we will have an ample Q&A period, so you'll be able to ask all of your questions. Thank you.
Okay, thank you. It's a pleasure to be here. And have to say, one always loves to see one's book filled with little tabs showing that the things actually were useful. So yeah, I'm going to talk about taking a scientific approach to teaching. This really represents the work of many different researchers, a few, some of which are from my own research group. Now, the way I'm going to organize things today is to start with an introduction, sort of laying out what I see as the important educational goals and some basic principles of learning, then talk about applying these principles in the undergraduate classroom and measuring the results, and then at the end, depending on time, make a few comments on sort of follow-up stages, either in both institutional change or particular things that faculty can use in short term. So before I get into this, I want to give you a little bit of background on how I got involved in this education work, and as you can sort of see the perspective I'm coming from, which is, it didn't come from my classroom teaching. There I sort of taught like I saw everybody else did, and I didn't think it was very effective, but I didn't really know anything else could be done. Actually, what changed my thinking on this was working with my atomic physics graduate students. I worked, blasting atoms with lasers, a lot of small groups, close interaction with graduate students. And I saw a surprising phenomena, puzzling phenomena, which is these students graduate students came into my work in my research lab. They'd had many years of great success in, science and physics courses, but they really didn't know how to do physics when they started working for me. But after just a few years of working in the lab, they had turned into physicists, and so it wasn't anything fundamentally flawed about them. And so after I'd seen this happen enough times, I said, no, this wasn't just a quirk of individuals. There's some fundamental question here. And so I tackled it as a science question, and I went in to look at the research on how people learn, particularly how they learn physics, and there was a body of research that I could use at that point. And from that, I came to understand this actually wasn't puzzling, this made a lot of sense. And I realized there could be much more effective ways to teach, and it actually started me almost 30 years ago, actually doing research on the teaching of science and realizing you could do, controlled experiments, you could have fundamental principles that would predict what's going to happen. So from my perspective, intellectually, actually very much like doing physics research. And so for some decades, I had 2 parallel research groups. Okay, so the rest of my talk is kind of, what I learned from all that. But I want to move to the educational goal and step back. And what was it that my graduate students, I felt, were, failing to learn from those courses, that they would show up when I asked them to do research. And it was really, thinking like a physicist. But what that really meant was in a real authentic environment, being able to make decisions like a physicist would when faced with research questions and conclusions and so on. And that really leads, I think, to thinking about, well, what is the ultimate goal of university education? And I would argue that it's really the bigger picture of this, that really we should think about our goal for students is to have those students, as a result of the education we provide them, learn to make better decisions, okay? And what does that mean if you then go down to the individual course or program level? It's really having them realize, when it's a relevant context, first recognizing that that's really relevant to what they know, but then in that context, being able to use the knowledge and the reasoning process of the discipline, the experts in that discipline, to make decisions with limited information. And I stress the limited information because if you've got complete information, then it just becomes a procedure. It's just a recipe. Computers will do it for you already. It's when there's not sufficient information that is when the expertise of the discipline really comes into play. And so that's what I would argue is that you want your students to be learning. And that's, in the rest of the talk, I'm really going to focus on how you teach and measure that kind of learning. Now, because I really want to stress and have you focus on this aspect of learning decision-making as a key educational goal, I'm actually going to give you 30 seconds to reflect on this, to prepare you for the rest of the talk, of trying to think about how experts in your discipline, i.e. mostly you, the kinds of decisions that you actually make in your scholarly problem-solving work that you do, okay? And just to give you a little bit of a starting point, I mean, I'm quite sure that every field has a set, has to decide on what suitable evidence or information to bring to bear on the problem I'm working on. And every discipline has, decisions about what makes a good scholarly argument and what features go into it, right? Okay, so now you have 30 seconds to think about all the other things, and then we'll continue from there. If you want to talk to each other, you can. Okay, so if you were a group of students, I would have made you talk to each other and I would have listened in and picked up on it. But hopefully from this, you've thought about a bunch of decisions that your field has to make. And you've maybe even thought a little bit about, gee, are we really teaching students to make those kind of decisions, to think about subjects in that way, okay? Now, jumping on then, so over the past few decades, actually, there have been advances in 3 different areas of complementary areas of research that have really provided new insights on how to learn and correspondingly how to teach this complex thinking, i.e. making decisions like experts and having expertise. And it's the cognitive psychologists who study basic things about how the brain thinks and learns, brain research, and then the work that I and others like me do of actually applying these ideas, doing experiments in university classrooms. Now, the sort of big picture that I'll start with is really a paradigm shift in thinking about how learning happens, the kind of learning we care about at the university level. And first, the old and frankly prevailing in most of the current university teaching, even at Columbia, I suspect, is that these brains come into our classrooms and they're different in various ways, and then we immerse them in knowledge, and it soaks in to different amounts that depends on what that initial condition of the brain was, okay? Now, if this is the way you think about learning, then it's kind of natural that the primary educational focus then becomes first, think a lot about what's the knowledge soup you want to immerse them in. That's the curriculum, expose them to, and admitting the best brains, so they're going to absorb the most, and then, naturally, if things don't work out quite well, you blame the K-12 education system. Okay. Now, what the research says gives is a very different way to think about learning. That in fact, these brains come into the classroom not being very different. And in fact, it's the educational experience really transforms those brains according to what experience they undergo. And in fact, the brains change, this transformation, in response to intense thinking, and that produces in the brain improved capabilities. And I'll say that the intense thinking that changes the brain is far more dependent actually on the teaching methods than it is on the content that is, or curriculum it's exposed to. Now, just to expand on this a little bit, it's this idea that you need sustained, strenuous mental effort. It's now pretty clear this is a biological requirement, that in very much like if I want to build up a muscle, I need to exercise it, I need to do it strenuously over a long period of time. In response, my body says, okay, I got to make that muscle bigger and stronger. It's clear now the brain is doing much the same thing. We can actually watch it change as it's learning. It's forming new neuron connections to extend, actually growing new neurons in there. And this is building and sort of strengthening these, if you like, these neuron circuits that are helping them learn to make decisions. And the expertise really lies in this rewired brain. Now, we also learned that to reach a very high level, sort of, Columbia professor level of expertise, everybody requires actually thousands of hours of this kind of intense practice. Again, that seems to be likely just a basic biological requirement to get the changes needed. Now, we can actually see this, and this great things about new brain imaging here, an example of two people interpreting an X-ray image here, and while they're having functional MRI. And so one of these people is a medical student who's just learning about this. The other is a highly expert radiologist. And you can see how their brains are doing very different things in this process, just as I was showing you. Okay, so that sounds pretty, exotic. But I think I can put this in a little more mundane terms, which maybe doesn't sound so radical, which is if you want somebody to learn, including yourself, how to make good decisions, which of these two ways do you think is going to be most effective? Sitting being told that, okay, if you ever run into this situation in the future and actually recognize it is like that, then here's what your decision should be, versus actually practice making the decision and getting feedback on that practice and learn from that and practice more, okay? Now, want to do a quick vote? How many think number 2 works better? Okay. Well, not everybody. So for those who aren't convinced, let me give you an example, which is actually quite an accurate comparison. Thinking about learning to find your way around a strange city, okay? And so you got 2 ways to do that. One is you can go drive around from a couple places and you have a person or a phone sitting next to you saying, oh, you want to go from A to B, turn right here, turn left here, turn right here. Or you can sit there and start out by trying to develop a mental map of the city, and then as you come to intersections, think about, okay, I need to turn here and why, okay? Many of you have been in that situation. In the first case, you don't remember anything, and it's because you didn't ever have your neurons have to be activated to do it, and so you didn't learn it. Okay, so the B is clearly right. So all of the fancy stuff we're going to talk about, research-based learning, et cetera, is really, at its core, the parts that work well is just doing that. We're giving students that kind of clear practice and feedback, okay? So let me move on to then applying these ideas in the actual instruction. And okay, there's a lot, now you get into a lot of details about how to do this right. In the center here, I have the learning that's taking place from practicing the thinking you want to learn, the decision-making you want them to learn, and they have to have good feedback while doing that. Good feedback means it's got to be timely and specific and actionable so they can see where they did wrong, what they did wrong, and how to improve it. But there's a lot of things then that go into have the design of these learning activities here. Along the top here, disciplinary expertise, their prior knowledge, motivation, and brain constraints, where the students' prior knowledge and motivation is where the variation across the students primarily comes in. And then down here, there's stuff about actually implementing this as a classroom. So I'm going to touch on, I don't have time to go through all of these. Basically, there's extensive research on any of them. I'll just pick a few examples. But I want to emphasize that, okay, all of these things matter, and we have good data that they matter and that they can improve learning. And so I'd argue that this really defines teaching expertise. It establishes, the research behind this establishes there are practices that research shows, you know, all of these things matter, and that if you take them into account properly, you will have improved learning, okay? And that's really a change, I would say, you know, from historical, even a few decades ago, to be able to make statements like that. So I kind of think that we're much like medicine was sort of in the mid-1800s, where you had doctors who were just, you know, doing anything they wanted, versus science, which now said, oh, there's actually things that matter that you need to take into account, you need to be an expert in. Okay, so let me go through a few of these, starting with disciplinary expertise. That's really has to go into defining the tasks here, the practicing thinking like an expert. And at some level, this is the ultimate justification for the research university like Columbia, is you got to have people who understand expert thinking here. So what sort of things go into that? Well, it's, you know, you kind of think about what the thinking skills, the decision processes, and I'm going to give you some examples from science and engineering that I know are quite generic across those fields. That first, when faced with a problem, a new situation, deciding what concepts and mental models are relevant and which are irrelevant to that situation, deciding what information is relevant, irrelevant, what's needed to solve the problem, deciding what simplifications or approximations are appropriate, and then guided by those things, deciding what are a reasonable set of potential solution methods to pursue. And then one continues down through that. My group has actually been systematically studying, and we find there's actually about 40 decisions that seem to be made consistently across all these different fields. Now, how those decisions are made, that brings in all the disciplinary expertise, but the fact that they are making the decision seems to be quite general. So I skip about 35 of them there, and then in the end, there are, once they get a conclusion or answer, all disciplines have very specific criteria to that discipline as to how to test whether those solutions are reasonable. So these are the things students need to be practicing, that to be experts in the subject, to make better decisions. I'll also point out, though, that if you think about the typical, you know, science and engineering problem, textbook exam sorts of things, you don't see any of these. They've been eliminated from what they're asked to do, and in doing so, you've eliminated from their education these absolutely essential components of expertise. Getting back to my poor physics graduate students, no wonder they couldn't do this. That wasn't what they'd been taught. Now, also, I want to emphasize again this point that it's really essential to not just have the decisions and know what they are, but the learner has to practice making them. And just to emphasize that, we just finished a paper in which we did a very carefully controlled comparison between one group two groups of equivalent students. One of them was saying, okay, here's a decision and here's the answer to this decision, what you should do with it, and some laboratory work. And the other group, here's a decision you have to make the decision about what happens now, the sort of scaffolded decision-making approach. And the follow-up studies were just enormously different as to how much students actually learned and how capable they were then of future problem solving in the area. Okay, so that's science, engineering. How many people here might have wandered in who actually aren't from science, engineering, math disciplines? Oh, okay, so a few of you. So I'm assuming you're wondering how much this applies to you. And I'll just spend one slide saying, I actually argue now, and I've written a paper that'll be coming out soon, arguing that in fact this applies to all academic disciplines. And the basis for that, which I don't want to get too bogged down into, is that the existence of an academic discipline and the standards of scholarship within them really contain a set of decisions and a consensus as to what a good decision is in that field. And so, to argue, you just have to go through what you see as a good scholarship in any discipline. You'll have a set of decisions that scholars are being evaluated on, and therefore, in the same token, having students practice and get feedback on those will give the same kind of results we get. And so, I'll just, here's a few things that apply to all the social sciences and most of the humanities that I can think of, deciding on valid sources of information, a way to lay out arguments, et cetera. So anyway, so that's just a quick note to the non-science engineering faculty here that I think people haven't been doing classroom studies of this, but if they do, I'd be strongly predicting you'll see the same kind of things we see in engineering and science. Okay, so talked a little bit about what has to go in there in defining the tasks. I'm going to skip over these. I think most of you kind of have a pretty good idea of the issues that need to go into this. You can ask more details later if you want. I'm going to jump to the brain constraints. This is something I find most faculty don't recognize. And there's really two big aspects here that are important. One is the issues of working memory limitations. So basically, when cognitive psychologists talk about the brain and memory, they divide up into two parts. One's the long-term memory. That's the thing that most of us think about as memory. It's got this enormous capacity and this, tremendous long-term, can remember things forever. But then there's the part that remembers and processes new information on short time scales, and that they talk about as the short-term working memory. It has this tiny capacity. Talk about something like 5 to 7 new items. Okay, new means it's not in long-term memory, and the more things that it's called upon to do, the more it reduces the processing and resulting learning, okay? Now, if you think about what this limitation like that is in any good biology lecture, if you look at the first PowerPoint slide, you'll have more than 5 new jargon terms on it right away, which if students pay attention to that means you can eliminate the rest of the lecture without any loss because they've used up all their brain capacity. This another way to a slightly more accurate way to think about it, this is just the number of things the brain can pay attention to at one time, okay? So this is critically important in what happens in a classroom activity, the short new stuff they're getting on a short time scale. One implication immediately is the idea of split attention, that when this tiny capacity is being split between, listening, paying attention to a lecture or something, and checking Facebook on their cell phone, looking on their computer, and so on. Basically, that just completely wipes out learning. So if you have a bunch of your students are doing that, you might as well just give up. You're wasting everybody's time trying to teach them there. And I find it's actually, I go around to standard classrooms, especially big lectures, and go in the back and look, and you'll see half the students aren't paying attention. You know, even if you don't believe anything else about what I'm saying, take my word for it, doing anything different will be improved learning because of that split attention being so bad because of this working memory issue. But there's some more subtle issues here, which is, you know, the use of jargon. When I see faculty put up some, you know, illustration of something and they want to pick something that looks nice, so there's a bunch of fancy, pretty stuff in the background just because it looks better, and maybe the jargon isn't that important, but can't hurt, it's easy to use. Not really, no, it actually hurts. Anything that gets students' attention reduces their capacity to learning. And the part that really gets students and faculty very excited when I point this out is those fascinating little digressions and those jokes that they you know, tell. Those are hurting learning. And faculty say, oh, how can that possibly be? That's the only time students are paying attention to me. And faculty and the students are saying, oh, how can that be bad? That was the only time I paid attention to them. And that's exactly the point. They'll remember the jokes, they'll remember the amusing stories, but it displaced the learning of the material that you wanted them to actually have. And so, you know, the bad news is if you want to put in a joke, it better be directly connected to the learning and the material, or it's going to actually reduce learning. Okay, the second aspect of this is concerns with keeping long-term retention. And ultimately, obviously, we want to teach students things, we want them to retain it for a long period of time. Well, it turns out, if you look at how long-term memory works, the problem isn't getting stuff into long-term memory, it's getting it back out when you need it, okay? And the subtlety there is that learning new material interferes with the proper recall of the earlier material. And so the classic way we teach is we cover, you know, chapter 1 and they study it and get tested on it, and we figure, okay, they've learned chapter 1, great, now I can go on chapter 2, 3, and 4, without realizing that the way the brain works is, as it learns chapter 2, 3, and 4, it puts in a bunch of new neuron connections there that interfere with the recall pathways on chapter 1. And so it's damaging the learning of chapter 1 in that process. And so, in fact, if you want good long-term retention and recall, what you have to do is suppress the learning, the interference as new materials learned. And so that means, so the way researchers found to do that is periodically they have to, covering other material, have to go back and recall and apply chapter 1 material that cleans up those interference terms that are coming in there. Okay, so then I'm going to jump down here to say something about implementation of this practice and feedback in the classroom setting. The two aspects here that are pretty critical is that exactly how the tasks are and deliverables and social learning. So the design of, you know, the students are having to work on making decisions. The task that calls on them to have to do that, we know there's some things that are pretty important just to make this work well. They have to have clear deliverables. And these accomplish several. One is they define the task, they have provide students a, you know, level of accountability that they're actually doing, having to do something, and they provide something that the instructor can look at and tell what the students are doing to optimize the feedback to them. In terms of social learning, basically almost every kind of good finding that has research behind it, in a classroom, people are having students work in groups of 3 or 4. That's by the way, if you don't know, beyond 4 is bad in most cases. But a lot of faculty, when they're first talking about this, they're puzzled as to how can it be better for the students to talk to 3 other ignorant students than hear me, the expert, explain it to them, right? And that's quite a reasonable question, but there's several reasons actually this kind of group interaction is beneficial. First is for individual students, there's many times when they'll just have some little thing that they're confused about, and they can get much more immediate, targeted feedback from a fellow student that will then keep them from getting stuck and behind and so on. So there's that immediate help aspect and makes the classroom more efficient learning for them. But there's another important and more subtle and interesting feature, which is that when people are called upon to teach something to a fellow, to somebody else, it actually kicks in a different cognitive processing. And so some really nice research showing that you can have people work real hard to learn something and they can do the best they can, and then you tell them, go prepare to teach it to somebody else, or you're going to have to teach it to somebody else. They don't actually have to teach it, but they have to think about teaching it. And in testing, again, they will learn more because they bring in added cognitive resources that actually enhance their learning. The brain sort of has some very specialized social, aspects. And then finally, there's another quite different purpose to this, which is that, if you're going to give effective feedback guiding student thinking, you need to know what that thinking is. And by having students be talking to each other and going around listening in on those conversations, you're getting a lot better idea of what's going on in those student brains, and so you can optimize your teaching and feedback using that signal. Okay, so move on to how would you actually put all these things in place in a real classroom. So I'll give you the example, this kind of practice thinking with feedback, and in the case where most people have thinking more difficult, a giant lecture class with 300 people in it. I'll do it for physics, but we've got good examples for all the other subjects too. So imagine I'm teaching introductory, first year electricity to a class this size. It's quite a realistic example, I should say. So what I would do is first I give them a pre-class reading assignment. Now, I don't expect them to learn physics, to think about physics from that, but I do expect them to get basic information from that without me telling them. They can get that as well or better from a book, and that frees up class time for more effective uses, okay? And then class doesn't start with me telling them stuff, it starts with a question. So, this light bulb and I give them this circuit with a bulbs and battery here, close the switch. They have to think about what's going to happen to the brightness of that bulb. Since I want to make sure I'm monitoring everybody and everybody's involved and essentially has a deliverable, they all have clickers, and so I record who they were and what answer they chose, and on my little dial up here shows all the distribution of the class. And then that's somewhat informative to me, but what is really most useful for is to have them to commit to an answer, and that really prepares them for further learning. And that further learning comes from, I don't show them the answer or in the distribution, they have to talk to the adjacent students around them and then re-vote. And while they're talking, that's like I mentioned before, I'm going up and down the aisle, listening in on those conversations, getting little snapshots of what's happening in those student brains. Then, after that, then I would demonstrate, show the result, but then have this follow-up feedback from the instructor going over which thinking and mental models are correct, and most importantly, which are incorrect and why. This is something I've learned from a cognitive psychologist, that where learning really takes place is not, oh, I got the wrong answer here, and now listening to the instructor explain what the right answer is. It's when you make something wrong, some thinking is wrong, and you then can understand what was wrong about that thinking and how you need to change it. And so it's actually much more important to go over why the incorrect reasons are wrong than what the correct answer actually is. And again, I stress this just because it's the opposite of what I see done in most classrooms. Okay, so if you think about the goals of this, you can quickly sort of see how I match this to prior knowledge and motivation and so on, but just focusing on how they're thinking like physicists in this case, how they're having to make decisions about what a mental model, a conceptual model of how electricity flows and how it interacts with light bulbs. They're having to decide how they can actually test that mental model. They're evaluating their arguments from their fellow students and deciding which parts of them are right and wrong. And so, basically, if I took out electricity and I put in, nuclear physics or condensed matter physics, for this, this set of activities is what physicists spend most of their lives doing, actually. So it's actually very much the authentic practice of being like physicists and making decisions. And while they're doing that, they're getting multiple forms of feedback to improve their thinking. They're getting it from the interactions with their fellow students. They're getting it by comparing their prediction with what the demonstration showed. And they're getting it from the feedback of me, the much more informed instructor now. Okay, so let me dash on now to okay, so I showed you principles, talked about implementation, but okay, what's really important is, does it work? So I want to show you some data. And so a few years ago, I actually went through and came up with about 1,000 different examples of publications comparing the traditional lecture approach to teaching with this sort of research-based teaching. And basically, the research-based teaching consistently shows greater learning, with the biggest effects being the more they target kind of the more expert thinking and decision-making aspects of that, and consistently shows lower dropout and failure rates. And big meta-analysis you can read if you want it. I'll just go through a few quick examples of this. This is work done at Cal Poly, where I like it because they have a whole bunch of different instructors in small sections, so you got good statistics. So this is the Physics 1 class that's basically the same every place in the world, covers the key aspects of this are force and motion. And so in this, we're testing these students, or they are testing them after they've completed this course. How well can they take some simple real-world situation they haven't seen before, like cars running into trucks, and use these ideas to predict behavior in the way a physicist would, okay? So we developed a good test for that. They collected data over a number of years, and basically, where all these instructors are scattered around this, on this test, a measure of about 0.3. That's we've got similar data from many classes like this now, and that's a pretty good level for a well-taught lecture class. Then they switched to this scientific teaching. Now students are, these are only 40 per section, so they're working in small groups, working through carefully, prepared worksheet problem activities, going ahead and having to answer and justify and make decisions with the instructor circulating as a coach during that process. And then they give those students the same test, and you basically see, on average, it's just doubled, and all the instructors are scattered around up there. So this makes a point, which I have other data to show you, but I want to really emphasize. You have the same instructors here, and they just adopt different teaching methods, and it produces much more learning, about a factor of 2 in this case. And so the key point here is it's really the teaching methods that dominate the learning, not any other factor about the instructors. Here's work from computer science. This is, again, multiple instructors. They're the 4 who taught the core introductory computer science courses or majors at UC San Diego. And they switched from standard lecture to something very much like, almost identical to the electricity example applied in computer science, looked at their drop and failure rates now, and they went dramatically down across the board. So again, you have the same people adopted different teaching methods. The result is about 1/3 the failure rate now that they used to have. an area that's just starting in this kind of discipline-based education research that's growing. We don't have nearly so much data on it, but now is looking at the effects on different demographic groups. We've got lots of data on the average. Now we want to start seeing how to optimize things for groups that maybe have been underserved in education in the past. This is work at Cornell, where they look at their big introductory biology course, and over a number of years they've recognized that the underrepresented minorities perform below the majority students in that class. And then they've introduced this research-based instruction, and that gap has now disappeared. Okay, so one more. So all those things we're learning over an entire course, but in a real course, you only have something happen in class, and then there's homework, studying for exams, a whole bunch of learning outside. This was a research question of just how much learning just takes place in the class. And so it was carefully set up to do that way. We picked there was a great big introductory physics course that had multiple sections of 270 students each. Picked 2 of those, which by a whole bunch of different measures were virtually identical. And the comparison was between the control class, which was taught by somebody who'd taught this material many times, very experienced and had high student ratings. And then the experimental class was somebody who was a relatively new PhD, but had been trained in my program on the principles and practices of this research-based teaching. And so these 2 instructors then agreed on to cover this on the same material to cover in the same amount of class time, 1 week of classes, 3 hours. I want to stress this because lots of people just assume it can't possibly cover as much material when you're teaching this kind of active learning, student involvement. And this was an experiment explicitly to test that if you had doing things in a reasonably optimized way. So I just want to stress that was looking to see if you could cover the same. And then they basically had the same test. It was a quiz given, a surprise quiz given right after the end of the last class to see, okay, what did they actually learn during that class? And it was timed so they didn't do any homework or exams, okay? Well, so here's the results. This is the test histogram, number of students versus their score in the test here. Now, you can see quite a substantial difference between the 2 here, but it's actually bigger than you think. The reason is, on this particular test, random guessing would give a student 3. And so you really have to sort of say the amount of learning is kind of how far above 3 they are. When you look at it from that perspective, first you see just how very little they're actually getting from a regular lecture. Now, I would have been shocked at this if I hadn't, about 30 years ago, done experiments on my own class like this, and found, gee, it was really depressing, but my brilliantly clear lectures were leaving most students leaving very little of the material. And frankly, any of you who don't believe this, think you're giving great lectures, you can repeat. This is really easy to do these things, but you better have a counselor standing by, because it's when you do, okay? But the other thing I want to stress here is, notice how the entire distribution's moved up. Because a lot of times people say, well, maybe this is better for the weaker student, but stronger students, they learn fine from lecture. And this says, no, this is really better for just the students who have a human brain, because that's how the human brain learns. And fortunately, that's the great majority of your students, I think. We also, in this particular experiment, measured engagement. No surprise, the engagement's much higher here. They're having to busy answer questions and justify things all the time, and that's an important aspect of learning, as I talked about. Okay, just quickly mention all that research. Most of it's been done on introductory classes. Just mention that a few groups now have been extending this up to more advanced courses, and my own group's been doing a lot of that. So just mention that applying these same ideas to advanced classes, and yes, they work well. Here's a standard deviation improvement, basically. And I'll just mention a few interesting features people have noticed at Stanford, because we've now, just in the last couple of years, transformed most of the physics major sequence, actually, 2nd through 4th year, to teaching this way. And the first thing everybody noticed, all the faculty, is, gee, students come to class now. That attendance is way up because students have decided they're actually learning more from it. And they have the response is very positive to this. But also the faculty response, when they've learned to teach this way, both the Stanford faculty, but also at this big program I ran at UBC in Colorado with several hundred faculty, the faculty, once they learn to teach this way, find it much more rewarding, and so they actually also are much happier teaching that way. Okay, so now, this is a question that I always get, and I'm sure it's in the minds of some people in the audience here, and none of you are rude enough to jump up and yell it out, so I'll ask it for you. It's, gee, I was taught by lectures, and look how successful I am, so traditional lectures can't be as bad as you say, okay? Well, I'll point out that this was exactly the same reasoning that was used to justify bloodletting as a medical treatment of choice for 2,000 years, okay? And the thing that people are missing here that's so critical is just, is what happened in the mid-1800s is you have to do actually scientific comparisons before you decide which is better. And so, you really, if you feel this way, you really have to go get a clone who goes through the other way of teaching, and I'd argue they're almost certainly going to be more successful than you've been. So, okay. So let me just, okay, I'm actually, timing's working out pretty well here. Let me just finish up on a few final comments here. This is something we see as better for students, and the faculty like it better. Okay, so how come it's not being done every place? We still filled, universities filled with lectures. And so I want to say a little bit about achieving widespread change on this. And then I want to leave you with a couple of specific things you can go home and use tomorrow. So this is mostly for administrators. This is referring to the book. This was a large experiment that we did on trying to change entire science departments, how they taught, and did successfully change, hundreds of faculty, and at UBC, most of the credit hours in science they offer here. And, it's a fat book. You can go read it and make me another 50 cents each, I think. But I just summarized the key results here, I think, which is, we showed it is possible. You can get in, research active departments, you can get an entire science department to change. And very importantly, when faculty do learn to teach this way, and it does take a non-trivial amount of time to learn with support, but they really greatly prefer it. And that's been a consistent message. And the key thing from an institutional standpoint is it really has to recognize there really is something that's, teaching expertise. You know a bunch of things and how to do it right, just like there's expertise in any one of your disciplines. And it's got to be recognized, it's got to be supported, and it's got to be incentives for the faculty and the departments to adopt that. And closely connected with that is really there has to be a better way to evaluate teaching, because the current system used here and every place else, student evaluation, does not do any of those things, okay? So I've written a book or paper on this where it covers kind of the key ideas, I think, in making a better evaluation system, talks about the weaknesses of the student course evaluations, that they really are, in many ways, they're unfair, they have bias built into them, they don't measure, they're not, when you look at the research, they don't reflect learning, and they don't reflect the use of practices that lead to the best learning. So, I'm pushing this getting this teaching practice inventory as a way of really having a detailed characterization of the practices being used and using that to evaluate teaching according to use of practices that we now have a solid research base showing what is actually better for student learning. Okay, so the last 2 minutes here, I'm going to talk about, I want to give you something you can take home and use, okay? And so there's a few different things here of what stuff of learning, sort of learning science research says on a whole variety of things where it's sort of your obvious intuitive ways to teach turn out to not be so great. And I can talk about many of these in the question period. I'm just going to go to the first one here, which in some ways is the most non-intuitive. It has to do with organization of how a topic's presented. So the absolute standard way, certainly in any science and engineering, social science subject, is you start out giving the formalism and the definitions and the equations, all these tools that people need, and then you move on to have them use those tools to solve problems, okay? Now, that's the standard way, and it's almost hard to imagine any other way could be. What could possibly be wrong with this? Well, it turns out nothing's wrong with it if the student had an expert brain like you do, but they don't. Their brain's quite different. And so for their brain, well, in the expert brain, this information comes in, this knowledge is all organized around tools to use, along with the criteria for where those tools apply and how to use them to solve problems. And so, that's kind of built into to experts thinking about it. But the students don't have that organizational system. So for them, all this new stuff comes in here. It's just isolated little pieces of information. They don't have any way to connect it, any way it's used. It gets organized as kind of a random bunch of pieces of information and, quite disconnected facts. And so they don't see it as useful for solving problems, and therefore they don't remember it when they need it. It puts much greater demands on working memory because it's rather than, a solid piece organized as, here's a tool chest of stuff for doing this. Here's 11 different things that I just try and keep track of. And it's very unmotivating because they don't know what all this stuff's good for. They don't see it as for solving. So in fact, this is why it's a bad way to present information. And the better way to do it is, again, somewhat non-intuitive. Start out with, here's a useful, interesting problem to solve. Now, they don't have the tools to do that. But if you actually give them, and there's subtleties in doing this, but you have them engage in trying to solve that problem, laying out so they can sort of at least dig into it, then they would notice the kind of key concepts and features that are important, and the research has shown can have a basic organizational structure, which then when you tell them the information and tools, they use that structure to assemble and use it. And so in some sense you're really literally preparing their brain to learn from the telling. It's more motivating, it gives a better mental organization and less cognitive demand, working memory, and so it produces more learning. There's this classic paper here led by Dan Schwartz, A Time for Telling, in which he shows basically teaching students the same thing, he's a cognitive psychologist, the same thing in the same amount of time. We're doing the standard way of, okay, I tell them all this stuff, and then I have them go off and practice doing problems with it. That's kind of normal. Versus, okay, first I give them this problem to solve. They struggle, they can't solve it, but they work on it for a while. And then he tells them the same stuff, and then measures how well they can do on other kinds of related problems. Gets a factor of 10 difference. in the learning. So it's really kind of amazing how big an effect that makes. Okay, so with that, I'll stop and we'll have time for questions and discussion for some time. I'll just give some conclusions here. I hope I've given you a sense that we have this new body of research on learning which really lays out teaching expertise that we can use, and when implemented, really has the potential to dramatically improve university education for the future. And frankly, I think our civilization sort of depends on improving education. And right now we're still largely using the pedagogical equivalent of bloodletting. Hopefully, we'll be rapidly moving beyond that. And if you want to learn more, I'll make sure my slides are available, but also these are some books, good references that I think is a good start. And then in here, we have a whole lot of resources on very specific implementation techniques of how to get students to do reading, how to do, assemble groups, the detailed stuff under instructor guidance. So thank you. Oh, okay, I'm going to cause trouble. It really slows things down when they got to run around microphones. This room's small enough, if you yell, I'll repeat the question, and that way we don't have this bogging down and chasing around with microphones. Yeah.
Can you give us an example of a question you might ask the students?
A question I might ask the students to discuss. I mean, the light bulb and the circuit one was one, but also.
Did you give them any kind of prompts that helped them with that? Like, how much would you have told them beforehand?
I can't give you a general answer here because that's always a very specific, to the students and to the context. And so a lot of times, I've been teaching very much an introductory course where what we're trying to do is have them use their past intuition and things they see in the world around them to see that physics is sort of not completely unrelated to that. So we've been giving them a lot of questions about, here's this problem to solve. Can you think of a real world behavior you've seen and relate that, just to think how it might relate to that, how these concepts might apply in that situation. So that's, that's one. But then when I'm teaching introductory quantum mechanics, it's much more like, here's what people observed about how atoms behaved. Can you come up with a model for what the electron could be doing that would explain that behavior? And oftentimes then, we would previously have considered a variety of different models of behavior, and they would have to try and argue which of these could or couldn't apply and how they might fail. So, but yeah, yes.
So can you give us a piece of advice to convince departments which are a little bit reluctant about changing from the behavior method into practice method?
Yeah, so question is, what advice can you give departments to convince them? That's a really, the quick answer is no, I can't give you advice. And the reason is that, that depends so much on the local departmental culture and attitudes. So, what we found from the book is I can tell you things that how an institution can send messages, pressure, incentives to departments to make it work. But then I can also tell you what kind of structures you need to have in a department to make this work once the department's on board to actually implement things. But in terms of actually convincing departments, like I say, that's too much of a local personality and culture for me to to tell you other than you got to pay attention to the local personalities and culture, and maybe go to the dean if necessary. Now, but let me actually expand on one little point there, which we found. I mean, I was surprised. I didn't expect this, but we found it was really critical once. I mean, in this program, we had a big competitive grant program to the departments could compete for a couple $1 million. That helped convince departments. But once they had bought into this, in terms of actually implementing it, we found it was really critical that they had new departmental structures to make it work. That in all of these departments, and we were to 14 of them or something, their old structures, you know, their associate chair for undergraduate studies or their committee for undergraduate education, those are really set up to keep the status quo, and they're really not good for making change. And you really have to have a new structure like an innovation committee where they have people and with responsibility and authority to make change as opposed to preserve status quo. That's really an essential feature to move things forward. Okay. Okay, yes, in fact.
As for the most textbook, I think organized with the standard teaching method. For your experimental based, research-based teaching method, do you use the new type of textbook or you
Yeah, so the question is about what kind of textbook to use for these teaching methods. And the answer is that, you know, textbooks are a real problem. And the biggest problem with textbooks is that if anybody has written a textbook or involved in this realizes that textbooks are not written to educate students. Textbooks are written to sell textbooks. And so there's a lot of things that the authors and the publishers put in that they know are bad for teaching. Particularly, they add all of this extra bloat stuff because it sells more textbooks, but it's really, you know, pretty bad for teaching. And so, so I don't know any good solution to that problem, frankly. You know, our economic system it just isn't set up for that. And so I don't really have any recommendations on that. In my own case, I kind of pick and choose, and I pick little pieces out of different textbooks where I want to use them, but I don't let textbooks be the guide. And I think that's the main advice you have to use right now is no textbook's going to be a good guide for you to teach this way. You have to look at them as a secondary resource you're going to use as best you can. Yeah.
Yes, hi. You had me at hello. So I'm right with you. There's one thing you never mentioned, I think not even once. Mind. You probably know Eric Kandel and Mind Brain Institute. You never use the term mind. You use cognitive psychology.
Right.
But I'm used to thinking that way as well, and you don't mention it. And could you explain that? At least explain that, how you conceive it or don't conceive it. Do you follow my question?
No.
You don't.
I mean,
You don't use a concept of brain and mind. Others do.
Yeah.
And I'm oriented that way.
Okay.
Do you see what I'm saying?
Yeah.
Maybe it's unfair.
Yeah, so for people outside, he's wondering, you know, what's my concept of mind as used by others? And I just have to say I haven't sort of gotten into that spirit. I kind of go, you know, with cognitive psychology and what they're talking about, what's happening in the brain, the way the brain's working, and so on. In some ways, that may be a more limited view than what people, but, you know, what you're talking about, it's just not something I've been thinking about. Yeah.
Hi, so you also had me at hello. I'm a learning designer, and I've been trying to encourage more of these methods among the faculty that I work with,
Yeah.
who traditionally teach in a lecture-based environment. And part of, I don't know if it's legitimate concern or avoidance, what I hear is the built environment
So the question is, what about the space and what constraints does space put on this? So, I mean, this is where I will kind of invoke unique expertise, because the Science Education Initiative, we came in quite specifically with saying, okay, you can't do, we'll give you all this money. You can't use it to spend on things that go beyond your normal expenditures, like changing space. You've got to think what you can do within the space constraints you have. And so my response to that is that more often it's being used, space is being used as an excuse, that we have good evidence of use of these teaching methods in any environment and producing substantial learning improvements in that environment. So, I will say, if you're doing it to a class of 250 students in a big theater, I'm not sure if trickier is the right word. There's more expertise required. There's a bunch of features that are more important to get right than if you've got 30 students sitting around tables, okay? So it's kind of easier to implement, but the fact is it can be implemented in any space and it will make a big improvement. And so yeah, I look at that as just, okay, you just have to go look at what people have found works well in that environment, okay? Now, I have to be a little bit careful here. I'll put in one caveat, which is that it gets particularly tricky above 300. And, I don't know, hopefully Columbia doesn't have classes that large, but it puts in some special demands when people on one side of the room cannot hear somebody on the other side of the room that I haven't seen a good solution to yet. So, but as long as it's, under 300, basically we know how to do it, and that should not be an excuse.
You made the argument that traditional lecture methods were not effective even in a previous era, so it's not the case that students used to be able to learn by listening to lectures and taking notes, and now they can't.
Right.
That's an argument that I hear a lot, so I was wondering if you could comment on any broad changes that you've noticed in undergraduates over the course of your career, if there are such changes, how that might relate to the methods that you're discussing.
You mean, so you're asking, are there changes basically in the student population or student way of learning that are relevant here? I mean, when people talk about, in the old days we learned fine that way. I mean, I just come back with saying, yeah, they said the same thing about bloodletting. There's no data on that. And more fundamental than that, we have sort of, basic theoretical understandings about, okay, you've got to use that neuron, and the more intense use of neuron, the more stronger that connection gets made. People sit and listen passively just aren't doing that, and they weren't doing it in 1800 either. So I'm very doubtful that the data would support that. But in terms of changes, so the brain hasn't changed. What has changed is probably the most relevant, actually, is the opportunities for distraction. Students would always daydream, but nowadays they've got sort of that, they've got those cell phones and computers actively sucking their attention away from class. So this is not research, this is just, speaking of which, of just these, opportunities for distraction. And so that's what I think would be the biggest effect. Yeah.
So I wonder if there are any reliable predictors of the brain's capacity to rewire for expertise. I mean, for example, does age matter? Do any other variables matter?
So here's a question about the brain's rewiring for expertise and what variables come in. And yes, age matters. It's not nearly as dramatic, less so than physical. The deterioration of physical abilities is somewhat faster than the mental abilities. But they see that, and there's actually something of a research debate going on now of whether past 55 people really gone downhill or whether they're still incorporating new neurons. So, you know, there are subtleties there, but what I'd say is there's some very dramatic things that happen in the first few years. The brain, you know, develops this massive amount of processing to language and then gets rid of all that and so on. And then it's relatively constant, but there's, you know, I forget the exact details, and it depends some on the cognitive tasks gets up there and then starts dropping off. And up here, people are still arguing about how fast it drops off. Okay, but it's more encouraging for somebody of your age. It's more encouraging than you might think in that there's still quite a lot of capacity to learn there. So, okay, way in back. Okay, you have to yell louder though if you're in your back. Yeah. Yeah, so the question is, does this work for graduate courses? So I don't know of any research. I have anecdotes on that, and actually I have a friend who's been teaching quantum field theory, which is kind of the most advanced physics course you'll ever find. And he found it worked wonderfully. And in fact, that's what we've seen. The people who've done this have found, you know, they've liked it, and the students have really liked it for graduate courses. I'm essentially, in many ways, I think it probably works better there, or the argument being what we've seen in these advanced undergraduate courses is, you know, you're closer to the kinds of things that students want to be learning to really what a really functioning, normal functioning physicist is thinking. So in many ways, it's kind of easier for faculty to come up with the right kind of practice tasks. And it's that step even easier for the graduate students. But that's anecdotal. We haven't really measured any real learning. Okay. Okay, just behind, yeah. So the question is, how well do I think online courses work, and what are the challenges? So, I mean, when I look at sort of what people have done and what the data on it, it's pretty dismal, actually. You know, it shows that, well, people do great with online courses if they're really well prepared and they're really highly motivated, okay? So if you're going to limit yourself to really well prepared and highly motivated students, you know, you sort of can not bother doing anything, right? And they don't work very well for others. Now, on the other hand, most online courses, they're just putting up lectures so people can watch them on a video screen instead of, you know, coming to class. And so you can be pretty confident what those are or aren't serving. But if I step back from this and say, okay, what could online learning accomplish? You know, and I look at what are the elements here that we know are essential for good learning. So I first would say it has to be synchronous. The idea of asynchronous, when the person goes and does something by themselves and does something and then an instructor comes by later, that's just not, that can't work because it can't provide the timely, specific feedback that's needed, and it can't provide the beneficial interaction with other fellow students, okay? So, but if I was to take, you know, an online course in which it was synchronous, there were groups that the students were either, you know, in person and hooked up, you know, 3 here and 3 over in, you know, upstate New York, hooked through a computer where they were interacting with each other. The instructor could drop in on those conversations in much the way I do in a classroom with, you know, adequate bandwidth so that you could preserve all the body language and so on, communication. It seems like you certainly, it seems possible to make it work as well. I'm still a little wary of an awful lot of the nonverbal communication of making sure that gets preserved. When you see students in a physics class, I can look at a physics class and know if they're engaged in the subject because they're making all kinds of hand gestures about how things are moving, okay? So, that's just part of their communication of that material. I'm sure in biology they're doing other things like that. So you'd have to make sure those things are getting preserved, but I think the technology is, if not there already, is very close to making it work. But in terms of actually implementing it in these ways that support principles of learning that we know are essential, I haven't seen people do that and actually run the studies on it yet. Okay. Yeah.
Thank you very much for your presentation. I've been trying to focus a lot on the process of what you're talking about, both as a student and as a teacher. And I have a background in biomedical research, and I'm a clinical social worker. So I'm sort of trying to think about this. What I hear is, at least in outpatient mental health, there is an epidemic of...
Just keep in mind, I'm going to have to repeat this question so those can hear it, and you're stressing my working memory here.
The two items you have to remember, the focus is going to be on the epidemic of metrics and the scientific method. And so I worry about this sort of, if I walked away from your lecture wondering what your thoughts are, is sort of scientific method and the things that we can measure being the only things that are valuable and I worry about, I don't think that's what you're saying. I also didn't hear about anything about relational aspects, social aspects of learning. You did talk about small groups. So
Yeah.
the relational aspects of learning between the teacher, students, and all the combinations, the social and cultural aspects of learning, and yet those, we can all operationalize everything and measure something, but the idea is, do you think about the fact that this relays the message that what cannot be measured is not valuable in the learning and teaching process?
So the question has to do with, are we measuring everything that's important? Are there other things in this? And also the social, cultural aspects. Let me deal first with the social, cultural aspects, because I didn't spend a lot of time talking about them, but they're really built into what I was talking about here. When I talk about, where's my nice picture? Sorry. I shouldn't have bothered. Come on, it's getting here. Yes. So in here, I'm talking about how the instructor is giving feedback, interacting with students, giving feedback, how the students are interacting with each other to make those things happen. We know a lot, that's not guaranteed that works, right? You can't throw 3 people together and expect them. So part of what you have to do in being a good teacher is really create and think quite directly about the classroom environment and what that environment means for the different students in that. We run little activities where they think about how to work most productive, how working in groups can be the most productive, and what norms of behavior you need to have to make that productive. And then when I'm, training faculty, we talked about how you have to interact with students to make I think as someone talked earlier about, making feedback so it's not threatening, and so it becomes normal to admit you made mistakes and talk about how you're confused. So those are certainly parts of teaching effectively, taking those into account. Now, in terms of whether things matter that you can't measure, so I have a much, much bigger view of what can be measured. And so there's an awful lot of things that people tell me that can't be measured, and I tell them, no, here's how to measure it, okay? So I, in fact, would probably argue that anything that you see as important in education, if one thinks about it carefully, you can measure it, okay? And if you can't measure it, ultimately, or if I can't providing a measure. I'd argue it's probably not important because it's just not going to show up anyplace. So, you know, if something shows up in some way, if you think deeply about it, you can figure out how to measure it. Now, you know, under what conditions, you know, that doesn't mean you can measure it by a final exam, for example. There's a lot of things that you need other ways to do things. But I'll still, you know, we could have this longer conversation, but I had it many times where people sit down and they list what they want, and I say, okay, so here's how we figured out how to measure that. Here's how we figured it out, and then after half an hour, they go away. Oh, well, okay, maybe you can't measure most things. So, okay, back. Okay.
I'm responsible for training all of our online instructors, and I wondered, you said that it takes about 50 hours to learn how to do active learning,
Yeah.
but I can't imagine I would ever get 50 hours in which to train faculty and adjuncts. What do you think is the minimum amount of time to get faculty to be able to implement this?
Well, you know, okay, so the question is, what's a minimum amount of training to get people so they're not too incompetent, you know? That's a measure of what your definition of acceptable competence is more than, so that number of 50 hours is really just, you know, it's not a hard and fast number, but it's where people have substantial support. What we've seen it takes. Frankly, I'm hard-pressed to think you can do a whole lot better than that. I mean, if we're talking about expertise in other fields, you're talking about 1,000 hours. And so here we're sort of getting people up to some reasonable basis of competence. It certainly depends on what they come in with, you know, how much they've thought about these things. I will tell you that, well, yeah, no, that was 50 hours. So I condensed things down into an intense 1-week thing. It wasn't great. I'm going to be testing a 3-day workshop where the 3 days are spread out probably over 6, and so they've got some extra time in there. But I mean, one of the realities I would say is of this research and of what the Science Education Initiative showed is that it's just not realistic to expect to have these, you know, half-day or 1.5-day workshops and expect people to get up to a very significant level of expertise in this subject. And I'll say that I see all kinds of examples at different universities I go around to, but definitely starting with Stanford, where, you know, they give people these things and they sort of give them the tools. They don't have the time to understand the details about how to set classroom norms, the principles behind them. And they go in and it's kind of like handing somebody a violin and a bow and telling them you rub it back and forth and expecting them to make, you know, reasonable music. You just have to set higher standards, basically, is the reality if you want them to reach a pretty respectable level. Yeah.
Thanks very much for your talk. I have 2 quick questions. One, do you see a difference between learning science and learning a foreign language? And the second question is, have you looked into your research into the new methodologies used for teaching a foreign language?
So the question is about how does this apply for teaching a foreign language? I would say this applies to teaching a whole lot of different things, but not language. And maybe it does, but there's a big reason for being very dubious about that, which is that the brain has a whole bunch of, so the kind of teaching stuff I'm talking about, you know, all the academic disciplines, the brain uses the same parts for that. But the brain has a bunch of very specialized stuff for language, okay? And so it's really, you know, from my perspective, it would be surprising if it really mapped over all that closely, just because it is just as a separate specialized cognitive issue.
How much time in strenuous decision-making is optimal before fatigue sets in and they're just not thinking at all anymore?
So what we have, so I'll just talk about what we've, so repeating the question, how's the optimum use of time in this strenuous decision-making going in? I think if I do this right, yes, okay, so now I have a clever way to get to the sections I want. Yeah, so this is a general structure we found works pretty well for courses at pretty much all levels. And so what we do here is, okay, they've done some stuff ahead of time, there's some introduction to the task, and then they're working through the task. And, in a small class, upper division, it's some, complicated calculation, worksheet, arguments, justifications. In a big introductory class, it's going to be a clicker question and discussion. But we find that, having them go for something like 10 to 15 minutes, no more than that, and then you have feedback, the instructor then brings people together, goes over, answers questions, brings people up to speed, and then they continue this. And this is we talk about resynchronizing, making sure people don't get too spread out and so on. This is enough time, so even the slowest groups have made enough progress that they can understand the explanation. So this is the cycle time that we've found. I won't claim it's optimum, but we'll have a lot of people just kind of find that works pretty well. It's a different question. I'm not sure if this is what you meant, but the length of a class session. And so most people find something that's longer than 50 minutes is just usually more convenient for making these things work. They can be made work on, I don't think I've ever tried shorter than 50, but they can be worked on that time. There's a question, though, about how long they can go. We don't really have any good data on this. We do have data from the studies of intense practice from, like, in musicians and so on, where they find the human brain just can't really stay focused for more than a few hours. It just gets worn out. We see anecdotally indications that everybody I've heard of, who, including myself, who's had a class that goes more than an hour and a half, that last half an hour, you're going up towards 2 hours, it's just conspicuously obvious that the students are just getting worn out. And so I think that's probably a pretty good estimate, just because everybody seems to find that. And, that is a long time for people to really focus intently. I mean, more than an hour and a half. So that's the advice I can give you now.
I wanted to ask about assessments. We talked about it earlier a little bit. Is there any research, or have you looked at the relative merits of, let's say, exams, essays, presentations, different ways of assessing students, and how frequently you recommend them?
So the question is, what's the recommendation on different forms of assessment? So what I'd say is, I haven't done a lot of research on this, but I know the research literature. And the research literature says that these doing it with a few high stakes, kind of sequestered exams is quite a poor predictor of learning. And you can understand why. It's kind of very artificial compared to how they'd be doing it. And that the research says that more frequent low stakes exams is better for learning. Okay, so that's, and then I guess, I remember one long review paper that argues that when people have kind of looked at longer term performance things which are in some sense more authentic, like big projects where it is something done over a long period of time and involves putting together lots of things, That's a better predictor of, more real-world performance. No surprise, it's more like real-world performance. So, so that's what the research says on that. Yes, trying to be geographically distributed here.
So if it takes 50 hours, right, to approximately to become proficient, right,
Yeah.
then you get to design and develop and implement and evaluate these new practices.
Yeah.
So on the continuum, right, if you look at it from like DIY to facilitated, what kind of institutional support do you feel is necessary, and sort of where does it land in here for this to be successful, on course level and department level? He's worked with, entire institutions and departments as well. So on that continuum, they put in the 50 hours and then there's so much more to be done. That requires lots of different types of skills, competencies, and expertise. It's a team effort, right? So where do you think is an optimal place there for institutions to aim?
Okay, the question is kind of what's the optimum use of institutional resources to support something like this? So we don't, what I'd say is we don't know. If I go back to here, this is the only large-scale experiment I know that sort of demonstrated substantial institutional change. And so what I would, so I'd say there's a couple of principles that went into this that I think one has to focus on, which is first, you have to focus on departmental change, because at any university like this, any major university, the department's the unit that decides what to teach and how to teach it. And so having programs, as most institutions do right now, where, random stragglers come in from a whole variety of departments and go through some programs here and then go back into a culture which is completely different than supported, just isn't an effective use of resources, because you're not changing their environment. And so I think one has to focus on departments, and then the institution has to think about how are they going to support departments to change. And there's and then you get into the differences of how the institution runs, and that's beyond me. I mean, I could wave my magic wand and say, well, all you have to do is the dean and the provost just say, okay, you're all going to start teaching like this, and you won't have any new positions in startup until that happens. Make it happen quite quickly, but few deans and provosts will do that. So, but if you did, that would be your optimum use of resources. But then you have to think what people can actually get away with and so on. But I think it's got to be departmental focused. It's got to recognize that, okay, there's real expertise here. It takes a serious investment of time, and we need to recognize and reward that investment. I mean, 50 hours is not enormous. I mean, most departments spend that much time in a faculty meeting each year, which is, putting in perspective. But it is significant, and it is if as Columbia and Stanford do, you basically the incentive system is all built about research. 50 hours mean you might write one less research paper and you'll be penalized for it. And so there has to be some system that counteracts, that penalty. Yeah.
So I teach a discussion-based research-based class for first-year undergraduates. One thing I have found challenging is actually to change the mindset of students, even if they are fresh people, but still changing the mindset from classic view traditional method to the new research-based method is very challenging. Do you have any opinions on that?
Yeah, so her question is about how do you change the mindset of the student. So there's two aspects to this which are quite important, and actually, so I'm going to broaden your question a little bit, because one of the things we found is that, I mean, faculty have two primary concerns. One is they're going to be penalized for spending that time away from doing research, because that's what, you know, research is what they get evaluated and rewarded on. And the second is that the students aren't going to like it, and it'll hurt, their student evaluations are going to go down, okay? So on the student evaluation side, what we did is we did some little studies to understand why students might not like this, and we found the main issue was when students kind of thought they were guinea pigs in some experiment the faculty member was doing, and so naturally that makes them uncomfortable. And so we basically have a script of how faculty should present these, and it doesn't mean first-year student, I mean any, you know, present these teaching methods to students when they're not familiar with them. And it's basically sort of a short version of my talk, talking about, okay, here's the research on how this is better to help your learning, here's data on this, so that, see, we're doing it for your benefit. So that's one big aspect, and basically what we see is, yeah, using that student evaluation don't change, which is kind of interesting in its own right, right? The faculty totally changed how they're teaching. In many cases, the learning is demonstrably better, and the student evaluations are completely the same before and after. But anyway, that's an issue of the student evaluations. That's different, which I think maybe your question is kind of the student's concept of learning has to be changed, okay? That's a more complex issue. And, you know, I don't have a great simple solution. What I will say is you just have to recognize and be sending that message consistently, and you have to make it show up in both, you know, the kinds of activities you do in class, but also the kinds of homework you do, the kinds of assessments you do, how you do grading of them. All of those have to be sort of part and explicitly talked about of, here learning, it means something different. We're teaching you to think like an expert now, not to get a good grade in high school. And so, you know, we have different higher expectations for you. But that's easy for me to stand up and say that versus, you know, making it work in the classroom. But it is just like convincing faculty to change how they're teaching. It takes time, and we see progressions over time with students as they sort of shift their attitudes. It's not an overnight thing. Okay?
So please join me